Okay. So good afternoon, everyone. My name is Markus Glück, come from the company InfraTec. I would like to tell you something about standard and lock-in thermography for inspection of electronics in integrated circuit. Some hints about InfraTec. So InfraTec is located in Dresden since 1991. It's privately owned. We have a staff of approximately 250 people. And our mission is we are specialists in terms of infrared technology, infrared cameras, infrared sensor. So what do we? We have the sensor division. We have the development of engineering production of pyroelectric infrared sensors. We have a large clean room for doing that. We are offering more than 50 standard detectors, analog digital detectors, and so on. For the thermography division, this is the division I belong to. We have research and development of infrared cameras, and these are being used for research and development, e-mobility, process and quality control. We offer customized turnkey solution, process monitoring, surveillance, preventive fire detection, and so on. But we offer training courses, thermography services, and software as well. Which kind of cameras do we offer in our portfolio? We have high-end camera for highest demands for research development. We have compact cameras where they are small, affordable. They can be used for simpler application. OEM camera modules, radiometric tune cameras, and system cameras. But we are not only offering infrared cameras, we are offering complete solutions as well for customers who would like to have a ready solution, not only the camera itself, they want to have everything. So we have a test bench for thermal rotate check, for electronic lock-in, press check, waste scan for observing waste in waste bunkers and so on, slag detections and so on. This is what we are offering and what we are doing of the company. So we are not only selling infrared cameras, we are doing a bit more. So I would like to show you some examples of passive thermography, and I want to show you, explain you the difference between passive thermography and active thermography. What can be used for what? Okay, this is a simple example of passive thermography. It is well known. It is only an electronic board with some devices on it. You put in some power. There some devices are heating up. They can be seen with the standard software and so on. This is standard thermography. This is well known. This is a well known procedure. Or on the other hand, other solution with electronic board with some emissivity correction, because you know that the emissivity of the object are having a huge impact on the measurement accuracy. So in the standard software, there are many tools included for emissivity corrections and so on. This is a standard procedure. Or what you see is here an electronic board, for example, and then you see the infrared image with a 640 by 512 pixels with a standard VHK resolution, with a standard lens, 25 millimeter, and with an instantaneous field of view of approximately 180 micrometer. But this one can be improved with standard passive thermography. When you want to have a better resolution, if you have smaller parts, when you want to see smaller energy distribution within the parts and so on, so you can have different lenses, you can have different microscope lenses, and here you see some examples of an electronic board and the electronic device with realized pixel resolution of 75 micrometer, and then with a dedicated microscope lens on the right side with 15 micrometers with magnification 1. But it can be improved as well. So here's another part of it. Here's a small resistor. Here's an image of with a microscope lens with magnification factor 3. Here you see an image with pixel size of 5 micrometers, field of view 6.4 by 5 micrometers. But it can be improved as well with the next step of microscope lens. Here's another one with 5 micrometers in image, and this is the next image with a magnification by factor 8 now. Here you see the temperature distribution of a resistor with a magnification 8 with a pixel resolution of 2 micrometers. Okay, but this is standard. This is not the critical point. Another interesting thing, I did it with my old iPhone. It's an old iPhone number 6. And here I grabbed an image with a microscope lens on the small button of the small fingerprint button. And here on the right side, you see the resulting image with it. This is the grid of the fingerprint button acquired with magnification 8 lens, but it can be improved as well. And here's on the right side, here's, for example, a standard image with magnification 8 with 1.25 micrometers. This is what can be done. Okay, what about active thermography? What is happening in that? One point is that passive thermography is you take the imagery or you take the radiation of the object that you get due to its own temperature. Okay, this is all information you get. You acquire it with the infrared cameras and so on, and then you do your imaging, you analyze it. Here with the passive thermography, you can achieve a temperature resolution of approximately 25 millikelvin or a bit lower. Okay? What is active thermography? Active thermography means I put in some energy into my object so that I'm heating up it a little bit, and then I'm looking with the infrared camera to the thermal response of the object. Okay? There can be a short energy input with no heat distribution, or it can be done with a tool called lock-in thermography. Okay? Or pulse phase thermography, but for electronics it's mainly lock-in thermography being used. Okay? For standard materials, let me say for standard metallic material probes and for other probes, what are you doing? It's, you have a test object, and then maybe you have a test object with a defect inside it, or a material inhomogeneity inside, but you don't see it on the top. So with the standard thermography, you cannot see anything. You don't see the fault. And then you can do some kind of acquisition depending on your object, depending what you want to do and so on. There are different acquisitions you can have. So electrical, ultrasound, induction, optical, whatever you want to do. So you're creating an energy heat in this object. It can be a single pulse, or that it can be a periodical signal. And so then you're creating a thermal wave. And so you can imagine when you have a defect or some inhomogeneity, then the thermal wave at the front side it will be slightly different compared to the other area. And then you are grabbing the image or several images with the camera, and then you do your analysis with the software. Okay? For example, for electronic objects, you can do an electrical acquisition, which means you can change the power supply, the voltage of the power, or you can put in some additional power, or you put in some additional sine wave and so on. This is depending on your electronics. And then you are creating a thermal wave within your object or within your chip and so on. Okay? This is looking like that. Okay, and then you are creating infrared radiation, and together with the camera, with the dedicated software, you can create your image. And then you see, okay, there's a difference. Okay, so what is important to know when you want to perform it, you need the lock-in, you need a periodically induced energy synchronized with the image, IR image. So it means that the excitation frequency and the camera need to be synchronized together. Okay? So what is happening? So when you put in some energy in your object with a dedicated frequency, you will create a thermal wave with a dedicated amplitude. Okay, so the surface temperature of your object is changing. Maybe when you imagine you are looking at the chip surface, and you put in the thermal you put in some changing electrical energy. The thermal answer will be that the thermal wave will occur with the same frequency. Okay? And for the correct calculation, both need to be synchronized and acquired. So you get some, with the lock-in tool, you get a thermal wave that is following periodically with an amplitude image for each pixel in the range of some millikelvin or down to microkelvin. And you get a phase image for each pixel. This is the phase image. This is due to the time delay of the thermal wave. Okay? And at the end, you can create between amplitude image and phase image, you can create a complex image. This is a pure mathematical process. Okay? Some images, or some example. On the left side, you see a standard image of a high precision SMD resistor. This is a standard image with standard passive thermography. But when you put in an alternating current, then you can see an image like that. So here you see the current density of the inside the resistor. And then you can imagine that maybe you can optimize your construction of the resistor and so on. Okay, there can be some hints of it. Or when you look at a chip surface, when you see here the chip, with a standard thermography, you won't see any difference because the signal of the thermal signal is often so low, or the emissivity factor of the object is so low that you cannot see anything. You cannot see any faults and on. But with active thermography and with the lock-in procedure, then you can see that there's a small difference, and it can be a hint to a fault. Okay? So it can look like that. Okay? Or another example, when we process a lot of images with lock-in means you are not acquiring only 1 or 10 or 100 images. There can be several hundreds of images, or maybe 1,000 images. But the more images you process with lock-in, the more and more sensitivity you can achieve. Okay, and this is an example of a chip surface that we apply only an energy of approximately 70 microwatts, and the thermal resolution will be 8 microkelvin. So the sensitivity will be very, very high, but the process will need some time. Okay, so how to do that? You need a software. We can offer this kind of software. This is called Active Online. So with this software, you will get 4 images. On the upper left side, you see the live image during the process and during the excitation and the control of the camera. You get an amplitude image as a result, a phase image, and the complex image. This is our software for doing this analysis. You have some device settings. You need to set the camera, you need to control the camera, you need to adjust the correct temperature range and the frame rate, and then with how many images we would like to process and so on. This will be done with our software. It is quite simple to work with it. Okay? this is only a small video about the chip. So on the left side, you see the live image. And on the left side, on the bottom, you see the small resulting hotspot that is occurring on this chip surface. Okay? And here you see it with the video process, how the defects occur, so that they can see them very easily, in which regions some inhomogeneity occur. Okay? Totally easy. Okay? Another thing is with our software that you can do as well. You can do some kind of merging with the live image and the resulting images, so that you can identify the critical areas on the chip surface, because everything is very, very small, so that you can have a quick impression in which areas the critical areas are present. And then you can think about your construction. Is it okay, or do you have to change your construction or something else? Okay? But for this kind of application, or for doing that, you need some additional tools from us, so we can offer additional components and hardware for excitation of the chips and so on. We can offer some chambers for it, so that the camera can put in, let me say, in a perpendicular orientation, and with the probe on the bottom, so that everything will be, so that the chamber can be closed for preventing some environmental impacts and so on. Okay? So this is a modular concept we offer. This is depending on the application, depending on what you would like to do, depending on the object you would like to measure. And so it's a quite flexible solution. And we can integrate different kind of power supplies for the chip, for example, from TDK, Keithley, and so on. Okay? So the chambers are required for preventing everything inside from environmental impact, due to moving people, due to other guys in the room, and so on, so that the environment will be stable during the lock-in process. Okay? And what we can offer as well, we can offer an XY table, manual or motorized. Let me say, if the chip is, let me say, if it's too large, and if you want to use a microscope lens, the image will be very small. And for the chip surface, sometimes you will need to create a lot of images, and then you need a tool called stitching for recombining the single image to the one to the big resulting image. Okay, and what we can offer as well, sometimes you would like to get a brief overview about your probe first for the chip surface, and then later on you would like to have a smaller view on the critical part with the microscope lens. Normally you need to change your lenses, so you need to open the chamber again, then you have to unscrew the first lens, then you have to screw the next one. And what we developed for that, we developed a new tool that is called a revolver. So here we integrate different lenses, standard lenses, microscope lenses, and so on. And with our software, you can control it. So it is turning the lenses for the field of view we would like to achieve, the field of view at the spatial resolution. And here in this revolver, we can integrate up to 5 infrared lenses in front of the camera. You can control it with the software totally easy. And the repeatability of the repositioning will be smaller than 10 micrometers. Okay? And this is another image where you can run in different modes, software depending on what you would like to do. Okay? But most important is that you need to have the correct camera. So you need to have a camera for with a high sensitivity, with a high battery resolution, maybe sometimes with high frame rates and so on. So we offer different cameras for that. So we offer uncooled cameras from this is our VarioCam series. This is a camera with a long wave infrared detector inside, uncooled. This is a system with 1024 by 768 or with 640 by 480 pixels. These are our standard uncooled cameras. But in addition, we offer another camera. This is our newest one. That is totally easy, totally affordable. This is called our Atari camera. It's totally affordable. This is a small one. This has a dimension of that. That is not too much. And in addition, we offer high-end systems. If you want to have work with high frame rate, with high battery resolution, or if you want to work with microscope with high resolution, we offer different cameras with different detectors inside, with different frame rates and so on, whatever you would like to do. But everything is being handled with our single software. It can be handled, all cameras can be handled by one software from us. And as told before, we do offer different lenses for different battery resolution, so that we can meet your demands in the best way. Okay? So thank you for your attention. This has been a quick, brief overview. So if you have additional questions or if you have something in your mind and so on, you can visit us at our booth. We are not so far away from here. Or you can call us, or you can send us an email and so on with the description of your application and so on. Okay? So